From 1998 to 2012, I produced a radio show and podcast called Change Surfer Radio. The show was eclectic, but its tagline was a sexy high-tech vision of a radically democratic future, and it helped shape the techno-progressive ideas that we've been nurturing at the IET. Many are still relevant today, and it's time to dust some off and share them again.
Today I'm speaking with Dr. Brian Marsden. He's an astrophysicist at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, and an expert on the observation and analysis of near-Earth objects, or NEOs. He's also a member and he's a vice president of the organization SpaceGuard Foundation, which is an international organization promoted the observation and preparedness for potential collisions with NEOs, with asteroids of different kinds. And he's the director of the Minor Planet Center for the International Astronomical Union. Welcome, Dr. Marsden.
Good afternoon.
Now, in the last year, there have been two major films and several TV films promoting the apocalyptic scenario of collisions with asteroids. And as well, there's been a great deal of research being done in paleohistory on the effects of ancient collisions with potential or apparent asteroid collisions on Earth. And can you tell us a little bit about how these the two are interrelated? The paleohistory seems to suggest that this has happened in the past.
Clearly, it has happened in the past. In fact, one can go way back to the mother of all impacts, which would be 65 million years ago, when probably something that's maybe 6 to 10 miles across collided with the Earth, probably near Yucatan, and caused the demise of many species on the Earth, including the dinosaurs. These other events that paleontology tells us about, many of them are fairly small events, and indeed they're rather questionable, I would say, in most instances. But some of them, even as recently as 1,500 years ago, little ice ages and that kind of thing, have been mentioned. But looking at it from the astronomical point of view, I mean, if we could have been hit 65 million years ago, and also there's plenty of evidence we were hit on numerous occasions before then, the point is that there are objects still floating around there, and from time to time they will come near the Earth, and from time to time, very rarely, moderate-sized ones will in fact collide with the Earth. The most recent collision of a moderately sized one would be something that was about 150 feet across that came in over Siberia in 1908. And it didn't actually reach the ground, but produced a large explosion, and the blast wave from that, the exploding body.
Is that the Tunguska?
The Tunguska event
Tunguska.
In Tunguska in Siberia in 1908. And we tend to think that statistically objects like Tunguska occur maybe once a century. We can argue whether it's once every 3 centuries or 3 times a century, because there's a possible evidence of a slightly smaller one over Brazil in 1930. It's sometimes a little hard to get definite information about these events. The 1908 event was noticed at the time quite clearly, even from the point of view that dust from the explosion was quite noticeable in the atmosphere over much of northern Europe. But the fact is, nobody actually visited the site of that impact or near impact for nearly 20 years. That just shows the problem in dealing with old events of this kind. Really, a relatively small part of the Earth's surface was populated in the old days. So if something hit, it often took a long time to find out anything about it. And by the time you got there, a lot of the evidence had eroded away. So we're actually a little hazy about some of these past events. So I, as an astronomer, tend to take the view that, okay, we've got objects out there that we can detect with our telescopes, and it's a question of calculating then whether there is any chance in any specific case as to whether something could impact the Earth, something we have directly observed could impact the Earth in the foreseeable future. By that I mean within decades or a century or so.
So you want to base the probabilities on a prospective study as opposed to a retrospective historical analysis?
That is true. I think you have to use a little bit of both, but you have to be careful that our statistics are biased. Both sets of statistics are biased, actually. Certainly the historical record is, but even insofar as the discoveries that we make, we know that we have not discovered a very large fraction of the objects that are potentially dangerous to us. If you suppose that something half a mile across is going to be really dangerous, the fact is we know less than 10% of those objects. And as you go down to smaller objects, like the Tunguska object of 150 feet, we know only a very tiny fraction of the objects of that size that could be a danger to us. But that shouldn't deter us. We should, I think, our best defense is really to make the searches, the astronomical searches for these things, and then we take it from there. Just during the last year, a very nice new observing program came online that immediately increased the rate at which we were discovering objects of this type by a factor of 5. It was a very dramatic increase, a kind of thing that hasn't happened before.
Who are the sponsors of that?
That is a program conducted by MIT's Lincoln Lab, which is here in Massachusetts, using a telescope in New Mexico.
Is that a part of the Space Guard initiative, or?
Yes, you might say that it is part of the Space Guard initiative. The program itself is called LINEAR, for Lincoln Lab Near Earth Asteroid Research. And if you look through the information that we put out about new discoveries of asteroids and comets, for that matter, you'll find that LINEAR has absolutely dominated the scene since about April 1998.
The idea that we were at risk of asteroid collisions has actually been batted around for 20 years or so, has it not?
Oh, it's been battered around for a lot longer than that. I think Edmund Halley discussed the idea that comets in particular might hit us when he realized what they were and the way they moved in orbits about the sun, and that's very nearly 300 years ago.
I guess Jules Verne had the famous Off on a Comet, which was based on the same premise.
That is true, and it took off from the Earth and came back and collided with the Earth 2 years later. That's right.
Yeah. So, but the idea in the 80s really got going when the international astronomical community decided to set up an observatory, or propose the setting up of an observatory network.
It's hard to say exactly what started the sort of modern aspect of this. Certainly, some of the people currently involved with searches, people like Eleanor Helene, at JPL, and Tom Burrells at the Lunar and Planetary Lab at the University of Arizona. Those two people, I think, more than anybody, have pioneered this work, and Tom Burrells was already interested in discovering these things clearly round about 1970, if not earlier, and Eleanor Helene became interested at that time and worked with Gene Shoemaker for a number of years on the project.
Of Shoemaker-Levy?
This is the Shoemaker of Shoemaker-Levy. Gene Shoemaker, unfortunately, was killed in an accident a couple of years ago, but Eleanor Helene continues quite actively with an observing program using a telescope in Hawaii. And Tom Gurrells continues working with the so-called Spacewatch project in Arizona, and there are a couple of other programs around the world. But this linear program has rather sort of come along and dominated things, particularly during the last year, as I say.
Superseded the other efforts?
I wouldn't say exactly that it has superseded them. I think that would be a little unfair to these other programs. The Spacewatch program in particular goes down rather fainter than the linear program. The great strength of the linear program is in the way it covers sky. It covers almost all of the available sky from the Northern Hemisphere each month, a couple of times, so that it's rather hard for something tolerably bright to sneak by. But Spacewatch does not cover so very much sky, but does go down a little bit fainter, and that's also very important. We need to balance sky coverage against how faint we go. That's the tricky thing.
And it seems there's also the tracking aspect of it, how many resources you devote to not just seeing an object, but also keeping track of where it's going.
That is a very important thing that is often forgotten. NASA, for example, has been very good about supporting detection programs. They do support the linear program, they do support Spacewatch, they do support Eleanor Helene's programs in large measure, but they're not very good at supporting the follow-up programs. The principal follow-up programs in the world are actually two programs in the Czech Republic, which does actually support that work. For a small population country, it's really quite a large per capita investment. Otherwise, most of the follow-up is done by amateur astronomers. There are many amateur astronomers now, maybe 100 or more around the world, who are really doing a great job in this area. Many of them are in the U.S. There are also large numbers of them in Italy and Japan and Australia. Australia is very important because we need observers in the southern hemisphere, and that, I would say, is one of our severe lacks at the moment. We don't have a search program in the southern hemisphere, and we don't have any professional follow-up programs in the southern hemisphere either. So we're very dependent on a handful of amateur astronomers in Australia and a couple more in Brazil.
In your Space Guard report to NASA, there were a couple options that were presented of setting up observation programs, and one of the options that you proposed was the establishment of an amateur network for follow-up observation. Is that something that's being pursued?
I don't know that it's being actively pursued in the sense of making a network. We talk about that a little bit, and yes, people like to cooperate, but I've always found in this business that people are very much individuals, and you can only sort of organize them so far. You've got to let them think for themselves and do things for themselves up to a point. Sure, many of them ask, what can I do to do something useful? And then we're happy to help them in that respect and say what we think is the most useful thing for them to do. But I think these are, after all, amateurs. They're doing it for the love of the sport. They're not being paid for it. And I think we very much appreciate what they do, but there is the danger we might take them too much for granted.
I've been encouraged, though, that this last couple months there's been the project SETI at Home, which is the search for extraterrestrial intelligence, and they're downloading Arecibo radio telescope data to screensavers on a network of 500,000 computers, and then the information's analyzed on the computer and emailed back to Berkeley.
Yes, I think that's a great example of what you can do with amateurs who do want to work together in some project like that. I suppose the closest thing we have in this astronomical area, or the NEO area, is by amateurs who download images, old images of the sky, and examine those old ones for possible currently observed NEOs, we can calculate where they were in the past, and this is something along those lines. Although if the amateurs have access to it, the professionals do too, of course, and there are some professionals working in that area as well. But I think in a way that's the same kind of thing.
I was very much struck in the Space Guard report to NASA. There was a table, which I suspect many people were struck by, of relative probabilities of an American in the course of their lifetime dying from impacts from asteroids compared to relative probabilities of other kinds of death. And asteroid impacts were just slightly less probable than an aircraft accident as a cause of death, but more probable than floods, tornadoes, venomous bites, fireworks, and so forth. And is that kind of statistic, I don't know whether that statistic is considered valid now, but is that statistic based on the fact that even though it's extremely improbable if it were to occur, it would be, all 250 million of us would go at once?
Exactly. That's exactly what it is. It's sort of averaged over the appropriate time scale. Chances are that there will be no devastating impact that will send 250 million people all at once. The chances are that will not happen during the next 50 years or even 100 years or more. But if it did happen, then obviously we have a problem. I think this is a sort of an extreme use of statistics where you're comparing things that happen every day with things that happen every 100,000 years.
Right.
And I think one has to be very careful in interpreting those statistics. I don't think we should say, though, that after all, the impact is so rare. If you're talking about a really big one in 100,000 years, we shouldn't ignore it. I think that is the danger, that if we get a little blasé about it and say, well, it's not very likely to happen, so let's forget about it. So I think that's one of the reasons that the people who compile these statistics are sort of drawing attention to it in this way, and sort of in a way letting the reader take the statistics how he or she wishes. There is the point, of course, that if we do carry out the searches, and we do find, let's say, 90% of the half-mile, kilometer-sized objects. That's NASA's goal, actually, to do that. We should also find some of the smaller ones, a smaller percentage of them. But if we can get essentially all of them, then that should, and study them so that we know whether they are going to come close during the next decades and centuries. I mean, we do need to, the danger is not to do the follow-up. As I said before, NASA has been a little reluctant to support the follow-up programs after the searches. But if we do that, then we're dealing with a problem that we can solve. Either we will find that there is, with very high probability, a specific object going to hit us at a very well-defined time, or we won't. If we find that there is such a thing, I hope that we find the date on which it's going to happen many decades ahead, 30, 40 years, something like that. I think there would be nothing more troublesome than to find that something is going to hit us in a very short period of time, like only a year or two or less.
No, the prediction that these objects would actually impact with Earth seems to be trickier than many of us would have suspected, given that Earth is on a circular orbit and these things are on elliptical orbits around the Sun. There was the incident last year. Was it NF-11 or
1997 XF-11? Yes, I know that well.
Yeah.
But the point about that is a very good example, actually, because it was largely misinterpreted what the danger of 1997 XF-11 was. Here we had a 1 mile object. We presume it's a 1 mile object. It had been under observation for about 3 months. And yes, it was going to come very close in 30 years. It really wasn't much of a consideration that it would hit us in 30 years. It was a mistake to dwell on that. The point is that it was coming close to us in 30 years, and there was some uncertainty. So it's a question, what was the object going to do after that? And that is why we needed to study it, because as a matter of fact, based on the information that we had at the time that announcement was made in March 1997, there was a possibility that could hit the Earth in October 2040. In fact, it's recently been calculated that the probability, based on the information we had at that time, was 1 in 50,000 that it would hit us in the year 2040. Now, 1 in 50,000 may not sound much, but it's the highest probability we've ever calculated for an asteroidal impact. And bear in mind, this was a 1-mile object. Mm-hmm. Now, unknown. The point is, how does that fare with unknown 1-mile objects? There, we're reckoning that in any given year, there's a 1 in a million chance of a 1-mile object hitting the Earth. So you see, it was up about 20 times above the background. Mm-hmm. Now, we didn't really know that at the time. We were in the process of analyzing it, and people immediately were jumping to the conclusion there was no problem in 2028. So what happened was that it was good, because we drew attention to it, and this caused an astronomer, Eleanor Helene, in fact, to examine her old photographs that she had from 8 years before. We gave the information where it would be 8 years ago, mm-hmm. and she, as a result, found images on her photographs at that time, thereby changing the period of time we'd had it under observation from 3 months to 8 years. That would bring about a dramatic improvement in the calculation of the orbit, obviously. Mm-hmm. And we could say, indeed, it would be more than twice the distance of the Moon in 2028. And furthermore, we could also say it could come not within 8 million miles of the Earth in 2040. And in fact, we also knew the orbits of the objects are moving away, so we could say categorically that that object would not be a problem during the next many thousand years. So that particular problem was solved, and that's great. We need to solve problems like that by finding old photographs or doing the appropriate follow-up observations. But that calculation that I did a year ago sort of started a trend and is now getting other astronomers paying attention to this problem. And during the last few months, we've had another case called 1999 AN10. Now, that made the newspapers a little bit, but not in the way 1997 XF11 did, which is good that it didn't make it in quite the same way. But it has come to the attention of astronomers, and that is what was important. It appeared that in April, when this was brought up, there was about a 1 in 10 million. 1 in 10 billion. Is that right? 1 in 10 billion chance that it would hit the Earth in 2039. 1 in 10 billion, which of course is not very much at all. But then, as we got more observations, usually when you get more observations, you tend to find that probabilities like that will just disappear, the same way it happened with 1997 XF11. Mm-hmm. What happened, though, when we got the more observations a couple of months later, things were bang on. That the uncertainty was greatly reduced, but that 2039 impact was still in the cards, but its probability increased to 1 in 100 million or something like that. It was increased by 100 times. Now, still, that's a very small probability. But when you see a sudden increase in the probability as you get more information, yes, you get a little bit worried, and you say, I'm going to have to get still more information. And we're still in that situation of getting more information that I hope we can do during the next 5 or 6 months, so that we can more definitely say what that object is going to do. We know that even if it isn't a problem in 2039, and chances are it won't be. There's actually another possibility for it in the 2040s when that could hit us. And again, we're about at 1 in 500,000 probability on that. So we are monitoring that situation, getting more observations, and we'll watch that object very carefully. But if it is going to impact us at any time, and that could happen even during the next 6 centuries, we know that that particular object is relatively dangerous for the next 6 centuries. And so we need to continue to monitor it. But as we do that, we will always find that it is never going to be a problem within 4 decades, let's say. Even if we're looking at it in the year 2100, and we would be sure at that time that it could not be a problem before 2140 or 2150 or something like that. We would always have enough notice so that if it should happen that object really is going to hit us, we would be well aware of it for a long period of time, and we still wouldn't be absolutely sure that it would hit us in 40 years, but as we then will continue to observe it, and maybe 20 years ahead, suppose we do find that yes, it continues to be a specific threat up to 20 years into the future, we continue to observe it, then at some stage we would then, but not before then, I think, decide that we need to do something about it. And
you address
that would involve missions out to look at it, which could have, in fact, have begun earlier. But if we're ever going to try and deflect it or something like that, obviously we do have to be very, very careful and not do it more than 20 years ahead, because you really want to be sure that it is a threat. You don't want to deflect something and find that it wasn't a threat, but now it is. So I think this is the way we have to think about the sort of mitigation against asteroids like this.
Is what you just referred to what you call the deflection dilemma?
It's sort of a deflection dilemma, yes, because again, the smaller objects, the smaller objects have you can calculate that you're likely to find one that has a higher technical probability of an impact in the near future. You could find one that maybe would have, let's say, a 100-foot object or 150-foot object. You might conceivably find that it has a chance of 1 in 10 even of hitting us 20 or 30 years from now. And the problem is that the object will be so small, and you would have observed it, therefore, for only a relatively short period of time from the Earth, because it's faint, and you can't, there's a limit to what you can do from the Earth, that in such a case, yes, you would have a little bit of a dilemma. You would, if you're seeing probabilities like 1 in 10, even for a very small object, not one that's going to do global damage, but that if it did make it through the atmosphere or close to the Earth's surface, would make a big crater or a big explosion, as the case may be. That, I think, is the dilemma in a way, because let's face it, you're not going to be able to observe that object from the Earth anymore. You're going to need to know fairly quickly that it might really be a problem. So you sort of in a way are forced to send space missions out to have a look for it. After your initial assessment. Even so, chances are it won't hit us. But I think that's really where the dilemma comes in. With the large objects, I don't really think we're likely to have a dilemma, because we can continue always to make further observations from the surface of the Earth, which is the cheapest way to make observations. But I mean, if you're talking about sending out space missions, that's a large amount of money that you have to put aside for it. So that's the way I see the dilemma, if there is one. There always is the point that if you go to very small objects, like 30 feet across, something like that, and we have seen such objects out in space like that, something that's 30 feet across will almost certainly burn up in the atmosphere, and anything that lands would be nothing more than a tiny meteorite, football-sized thing, that sort of thing. So you don't have to bother about the very, very small ones, but there's sort of an intermediate range where it's tough for us to get information, and we could conceivably be in for a nasty surprise.
Well, your work is, I'm tempted to say that it has a very small chance of being the most important work on Earth, which makes it probably very important work. But in any case, it's fascinating work, and if people want to learn more about SpaceGuard's work, if you type in SpaceGuard in any search engine on the web, there are a number of SpaceGuard documents, and every country, industrialized country, seems to have a SpaceGuard site up.
That's right. The U.S. actually does not have its own SpaceGuard per se, but there are organizations with an interest in this. But SpaceGuard UK, I know, is particularly active, and we work quite a lot with the leader of that is also on the board of directors of the international group to which I belong.
Mm-hmm. And I've been speaking with Dr. Brian Marsden. The website for the Harvard-Smithsonian Center for Astrophysics has several links about Dr. Marsden's work. I thank you very much for being with us today.
You're welcome.